Science time. We're gonna talk about
Oh
magnets. Let's call it. It'll sound more professional if we call it magnetic force. Ooh, that's nice. Magnetic force. Magnetic force. You know about the magic of the magnet.
Yes.
The magic of the magnet. What is the magic of the magnet? Yeah, Hunter. What's magical about magnets?
They can attract and repel each other, and if you why I think is really cool is that there's stuff they've made where magnets can repel each other and stuff can float because the magnet.
Oh, check it out. The magic of the magnet is how it does stuff that we are not used to doing, right? Things are wild about magnets. If I drop a normal object, magnets are normal objects. It's not really magic. When I say magic, I mean the unexpected stuff that happens because of science, right? It's the world. It's the real world. This is the way the world works. This is one of the things I'm always trying to tell you that maybe when you are, I don't know, Wesco employee, railroader, lawnmower, whatever you're going to be when you grow up, homeless person, whatever you're going to be when you grow up, maybe it's not important to you that you know about Newton's laws or magnets, but what makes your life magical, what makes your life cool and worth living is knowing stuff about the way the world works. This is why you're here, is to explore the world. If we have a normal object, magnets are normal, remember this is science, not magic, but it's cool because if we have a normal marker object, gravity was an unbalanced force acting on it, so it accelerated toward the ground. A magnet, there's more than just gravity going on here, right? Okay, you're not supposed to drop those. There's more than just gravity, because if it were an object that was non-magnetic, yes, it would fall only because of gravity. That's the only unbalanced force acting on it. But because of this, there's something else going on here, right? So we know there must be another unbalanced force, because it's not just, here's a normal object, which is marker. Marker, I'm going to label it because that's not what markers look like. What forces are acting on the marker as it falls?
Gravity.
Gravitational force and then
a little bit of air resistance. So we'll call this F sub D for drag, F sub G for gravity. On the magnet,
there's
F
drag
sub G.
and gravity.
there's still F sub D. There's still, I'm going to put, why would I make the arrow longer for F
Because
sub
it's heavier.
Because it's heavier, it has more weight.
And then there's a magnet.
And then there's
Magnetic
also a magnetic force, F sub capital M, which is attracting it to what?
The whiteboard.
No, yeah, the whiteboard, only because the whiteboard is here. What? Now what? No, hold on, before you answer. What force must also be acting on the whiteboard?
Gravity.
A gravitation.
Yeah,
No.
sure. Gravity,
A normal force?
F sub G, F sub F, which is friction. It's actually friction holding this on because of the nails. But anyway, what else though? The board. On the board. The board is being acted on by the magnet too.
By magnetic.
Yeah, look, here. I don't know if you can see this. I assume in the video you can.
Is that a strong magnet?
Oh yeah. You see the board though? Do you see what the board is doing?
Yeah, it's getting closer to it.
Yeah, the board is coming up too. So just what does this kind of remind you of? I'm thinking of two things. Which of Newton's laws does this remind you of?
The first one?
The third.
Newton's third law. For every action, the action being the magnet pulling on the board, there's an equal and opposite reaction. The board pulls on the magnet. So why does the magnet go toward the board and not the board come toward, well, first of all, the board does come a little bit toward the magnet. But how can the magnet go swoop?
Because the magnet's stronger.
No, it's the same exact force.
Because the force is acting on the whiteboard.
Yeah, because the magnet has, first of all, it has less mass, and so therefore less inertia, so it's able to accelerate more. It's still F equals ma. Same exact force on the whiteboard and the magnet, right?
Yes.
The whiteboard, magnet. The whiteboard has a great big mass, not that big, but it's also nailed onto the wall. So it accelerates a tiny little bit. The magnet has a smaller mass, and so it accelerates more. Just like we talked about with Newton's third law, right? So magnetism must be a what?
Unbalanced.
Not always unbalanced, but magnetism is an example
Acceleration.
No, magnetism is an example of, say, the other thing. Not necessarily unbalanced.
Force.
Yeah, it's a non-contact force. It's a force. Magnetism, so the magic of the magnet is, it's a what? A
non-contact force.
Yeah, well, specifically a non-contact, but it is a force. A non-contact force. In fact, it is one of the four what we call fundamental forces of the universe. The four fundamental, what's fundamental mean? Huh?
Like
The way you do
basic.
Yeah, basic. Basic. There are literally only 4 forces in the entire universe, and they are these. I'll get you in a second. Okay. Strong nuclear, electromagnetic, weak nuclear, and gravity. These are the only 4 forces that we know of in the entire universe. There are literally 4. What about all the other crazy forces we say? What about the normal force? What about friction? What about drag? Well, actually, those 3 things I just listed are all types of electromagnetic force caused by the atoms, which have electrical charges, not necessarily touching each other, but being in each other's magnetic fields. On the microscopic scale, these are the only forces. All other forces are some combination of these. Yes?
What's number 1?
Strong nuclear. All of these are strong nuclear force, electromagnetic force, weak nuclear force, and the gravitational force. So what's the magic of the magnet?
What's the second one again?
It defies gravity.
Yeah, okay, it can. It can seem like it's defying gravity. Does that mean it has no weight? Gravity's not acting on it?
No.
No.
You drop it off
It's
the
just
floor.
that sometimes the force of magnetism from this magnet acting up can be stronger than the force of gravity pulling it down. So it might seem like it defies gravity. Remember, it's not actually counteracting gravity. It's just
stronger.
Yeah, it's just stronger in a different direction from gravity. Got your question.
So is there a difference between gravities like in this normal air and gravity and not gravity, magnets in this normal air and magnets in water?
Okay, yeah, let's talk about that. So why might a magnet behave differently in water?
Because there's a very small gravitational force acting on it.
Not the gravitational force would technically still be the same, but there's also a buoyant force that water pops up, and there's also more drag. So yeah, there would be a difference in magnets in the water, but actually because of the friction force, not because of the magnet itself.
What's the third one again?
Weak nuclear force.
What's the second one?
Electromagnetic. Yes.
I have 2 questions. If the Earth didn't have a magnetic like field,
Yeah.
would magnets work on Earth?
Yeah.
They still
definitely.
would.
Yeah, magnets are a completely different thing. The magnetic field obviously has to do with magnets, but this magnet doesn't have properties because of Earth's magnetic field. It has properties because of its own magnetic field.
So like if the Earth's magnetic field somehow went away, that magnet would still stick
Yes,
to it.
definitely.
Also, what is the magnetic force? Is it because
We're getting there in a second. Yep, that's exactly what we're going to talk about next. And William, I want you to ask your question, which is relating to what Hunter said next. But what is your question right now?
Can I short term?
Yes, of course. I'm erasing these diagrams, so you can still copy down the 4 fundamental forces of the universe, because I understand some of you are probably still on it. The magic of the magnet is that it's a non-contact force, so it can seem like it's floating, because we're used to forces that only act when they're touching, or gravity, which we interact with all the time. But then the magnet has a non-contact force like gravity, but we're not always around magnets, so it seems magical, and it can who said defy gravity? Like Gabe said, it can seem like it defies gravity. Was that you, Gabe?
No, I said that.
It was Hunter. Okay. Anyway, here's how magnets work. All of this. Which of these, if you had to guess, just based on the names, which one are we talking about with magnets? Electromagnetic. So we're mostly talking about this one, the electromagnetic force. Based on what 2 words do you think the electromagnetic force is built from?
Electric.
Yeah, electric
And magnet.
and magnet. Exactly. So this force, this one fundamental force of the universe, governs both what we think of as electricity, which is all around us, and what we think of as magnets, which is actually all around us too. We just don't, it's usually on such a small scale that we don't notice it unless we have a magnet. We're going to talk about why that is in a second. And Gabe, I want your question now too. So yeah, Gabe, ask your question that you asked me the other day that I told you to remember.
Why are certain materials magnetic?
Perfect. Thank you for phrasing it that way. Why are certain materials, specifically iron, cobalt, and nickel, oops, that should be a little low, iron, cobalt, and nickel, and then there are some what we call rare earth, and then some rare earth metals. So why are these things magnetic, and things like hydrogen not? And the answer has to do with their atoms. You know that all stuff, all matter is made of atoms, yeah?
Mm-hmm.
You know what makes up an atom? No, molecules are actually made of atoms.
Just matter.
What makes up atoms?
Subatomic particles.
Subatomic particles, which include what, Fate?
Electrons, protons, and
There we
neutrons.
go. There we go. So in an atom, which very simply looks like this, in an atom, here are the protons and the neutrons. In the does anyone know what this thing here is called? We'll talk about this later on in the year, but this is the nucleus. And then the electrons hang out outside. Okay. The nucleus and the electrons interact with the electromagnetic force. Electrons have a negative charge, and the nucleus has a positive charge. So far, so good, right? I don't know if this is review or not, but this is a real crash course in it. What happens is that in some materials, specifically iron, cobalt, and nickel, and some rare earth metals, the electrons, because of the way the atom is, because of quantum mechanics in the atom, which we'll talk about when you're in chemistry and physical science a little bit, but just because of the way the atom is, the electrons hang out in one area more than another, which gives this atom a charge. So far, so good. So there's this atom itself has a charge. It's negative over here and more positive over here, kind of like a battery. Okay? You with me?
Yes.
Now in regular matter that isn't these things, the electrons balance out. Maybe at 1 second it's like this, but in the next second it's more negative over here, and so it balances out. But in the magnet, because of the spin of these electrons, it happens to be more this way than this way. Okay? And then even in there's examples of iron. This is not magnetic. This is iron, but it's not magnetic. It's not. I mean, I'm not. Whoop! It's not stuck to that. It doesn't stick to the whiteboard. I'm trying to avoid the actual magnet. It don't stick, but it is iron. So what happens in lots of normal iron is that the atoms themselves have a charge. I'm trying to draw it the same size, but maybe the next atom over, the negative charge is up and the positive charge is down instead of left and right. Okay? So what happens in a magnet is that all these atoms line up, so they're negative and positive line up together.
Protons and neutrons.
And this area of all these atoms lined up together is called a magnetic domain. And a magnetic domain is an area of matter where all the atoms are lined up in the same direction. Are you with me so far? Does anyone have a question so far? Will?
Are we gonna learn about the 5 different types of magnets?
Yep, we are, but right now we're learning about magnetic domains. You with me so far? You know what a magnetic domain is?
Yes.
It's an area of a piece of matter that has a magnetic, what we call pole. This
So
would be
not every part of that magnet is made of magnetic domains.
right. No,
There's
now check
still
it out.
normal atoms.
Now check it out. Yeah. So we could call this the North Pole, and this is the South Pole. They're still made of atoms. And then if we look at a bigger piece of matter, so I'm going to zoom out a little. Pretend I'm zooming out. Erase, 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 erase. You should be writing down the definition of magnetic domain right now.
Will you say it?
Yeah. What's a magnetic domain? Someone else.
An area where a bunch of magnetic
Yeah.
atoms.
Yep. An area where the atoms have matching magnetic fields. An area where the atoms have matching magnetic fields is a magnetic domain. So maybe if we look at a piece of, here's a chunk of iron. It's all shaped up into these magnetic domains. And each one of these magnetic domains, if this chunk of iron were life-size, each one of these magnetic domains would have billions or trillions of atoms in it, okay? Lots and lots of atoms in each. If this piece of iron were life-size, each of these areas would have billions or trillions of atoms in it, okay? Each magnetic domain has a pole. But maybe even the magnetic domains, their poles don't match. What has to happen to make it a real magnet is all the atoms have to line up to be in a magnetic domain, and then all the magnetic domains have to line up to be a permanent magnet. And that's one of the kinds of magnets that William is talking about. A permanent magnet. That's just what we call it. This might have a north pole and this might have a south pole. A permanent magnet. Does that mean it's never going to be unmagnetized? That's not really what it means. We just happen to call it a permanent magnet. So a magnet like this one, which has its own magnetic field, is a permanent magnet. Is the whiteboard a permanent magnet?
No.
No. The whiteboard does have a magnetic field, but only when there's a magnet around.
It's not going to stick to metal. Or like,
It won't stick to the wood at all. but it will stick to this. And so what's happening is the whiteboard has its own magnetic domains. Okay? They don't line up. I'm trying to make it so they don't line up. We're clear on magnetic domains, right? The whiteboards don't line up. So it's not going to attract other stuff. But then when the magnet comes around, which they do all line up, so it has its own poles, that makes these magnetic domains all shift so that they're in the same direction too. So now, for a second, the magnetic domains in the whiteboard do line up, and it attracts the magnet to it, and the magnet attracts it to that. Because of this thing called and it's shaped kind of like this, magnetic, write this down please, magnetic field.
So the whiteboard has a magnetic field, not a magnetic.
This has a magnetic field, and the whiteboard doesn't have one.
Oh, it doesn't.
But when I bring the magnet close, now for a second, this area of the whiteboard does have a magnetic field, and that attracts it. Fate.
Can magnets still attract each other even though there's an object in between them?
Mm-hmm. Yeah, it's a non-contact force. So even if they're not touching, they can still attract each other. Good question. Go ahead.
Like those blue things, how they can still erase the board, but yet they stick to
Right.
the
Yeah. So that's a good example. This has a magnet inside of it, a permanent magnet inside of it, but it's underneath this fuzzy part. So the fuzzy part is in between. Right now, it sticks, even though there's a fuzzy thing in between the magnet and the board. It's the same principle, except it has a little bit in between it. Even watch this. I don't want to put this on everything. Look, see, it's still. Can you see that? I'm gonna do picture in picture so that people watching the video can see it too.
Whoa.
Or even you do that. There we go. That's the sound magnets make. I'm also erasing. This is a great example of multitasking. I can teach you about magnets and erase using a magnet. All right. Anyway, come here. Magnets have to have two poles. Every magnet. Here's an example of a bar magnet. Every magnet has two poles. Always two poles. What happens if I chop this in half? Now it's two magnets. This one's only north and this one's only south, right?
No.
No, tell me why. What actually happens?
It splits up again.
Yeah, so this one's north and it has a south pole. This one's south and it has a north pole. Just like, here's Gunner. Here's his bottom and here's his top. We cut him in half, just like in Among Us. Now the top part has a top and a bottom. It's because the poles of a magnet are not real pieces of it. They're just orientations of it. We just talk about it as a direction. Even though Gunner's been split in half like in Among Us, the top is still the top of his top, and the bottom is now the bottom of his top. Yes?
What about my question from yesterday?
Let's hear it, Will. What was your question from yesterday?
Is friction and static electricity the same?
Yeah. Okay, so let's get to that next. When we think about static electricity, which is also the electromagnetic force, when things rub, here's a foot. Whoa.
Beautiful.
Ooh.
That,
And here's some carpet. And when you shuffle your foot on the carpet, there's friction, first of all. F sub F, friction. But it's also the little atoms that make up the carpet and the atoms that make up your foot are rubbing against each other, okay? What happens is some of the electrons from the carpet move to your foot. So now the foot has more electrons, so it has a partial negative charge. And the carpet has fewer electrons, so it has a partial positive charge. And then, when you touch your buddy, the electrons that were gathered up from the carpet to your foot move to your buddy, and that makes a lightning bolt. It is literally the exact same thing as a lightning bolt. You can hear a little sound, but right?
oh yeah, like with the blues and stuff.
Tiny little crack. You know, you've done this. Who has brothers and sisters?
Oh wait.
So when you shuffle across the carpet and touch them, you hear the noise of you shocking them, right? That is literally thunder. The only difference is the scale.
You mean lightning?
No, it's thunder. The sound it's making is thunder. It's just tiny.
Wait,
It's the exact same
thunder's made
thing.
from static?
Yeah, it's the exact same thing. Here's planet Earth. Here's the cloud. The cloud is picking up electrons off the ground, and then when it touches something else, zzz, it makes a zzz noise, except it's bigger, and so it goes boom, and it goes a long distance because it's bigger. Well, the only difference between these two things is the scale, and this is called static Let's spell it right, actually. Static electricity. Whatever. Fate, what now?
How can your foot have more atoms but have a negative charge and the ground have less atoms and have a positive charge?
No, it has fewer electrons, is what you mean to say. And the electrons themselves have a negative charge. And so if your foot has taken some from the carpet, now your foot has more, so it has a negative charge.
Oh.
Gunner. No. Okay. We have one more thing to talk about. Let me tell you what it is. A second, I have to remember. Oh, we talked briefly about this, but I want to talk about it big time now. Write down this idea of magnetic fields. Write down magnetic field, please. Magnetic field. Oh, I already have it written down up here. On a magnet, it looks kind of like, you can see it. Let me show you using this thing. You stay there. Here, I have this little, like, it's not going to show up very well on the camera probably. I have this, it's just some water, well, I think it's actually glucose or something, or I'm sorry, glycerin, and it has iron particles in it. Remember, iron's one of the things that can be magnetic. And if I put this magnet on here, can you see that? Well, first of all the iron's attracted to it, but it's attracted in a specific way. If I change it,
Whoa. So it's fundamentally ferrofluid?
well, it's not quite ferrofluid, but what we're seeing here, let me try to draw this as it is here.
They look like ants.
Here's the North Pole, here's the South Pole, and what the iron filings are showing us is this kind of pattern. I think actually this is the North Pole and this is the South Pole. I'm right. I'm right the second time. And it also does it in 3 dimensions. It's kind of hard to tell, especially it won't be visible at all on camera. But it's 3-dimensional. So imagine it's also doing this out of the board, and the whole thing is kind of almost like the shape of a heart. It's got these like loop-de-loops. And this is the same thing as Earth's magnetic field. The planet Earth is a giant magnet. Earth's magnetic field actually, though, because of the sun pushing on it, looks more like this. One of the magnetic field kind of blows out the back, because they're kind of pretty shaped. But Earth has a north and south magnetic pole as well.
Wait, but the South Pole of the Earth isn't the magnetic South Pole. It's just
There's a difference between the geographic South Pole and the magnetic South Pole.
Are they close though?
Yeah, they're very close. In fact, they're almost meaninglessly far apart. On the scale of Earth, they're something like maybe 20 miles away, but the whole Earth is much bigger than 20 miles.
Wait, so what throws it off? Isn't the South Pole exactly the most southern
It's
point?
because the Earth has a tilt in its axis. The Earth itself is not actually straight up and down; it's tilted, and so the core has a slightly different tilt from the rest of the Earth, and so the core spins in a direction perpendicular, but not quite perpendicular.
How did they track the magnetic?
I would assume they
South
just
Pole?
use compasses, I would guess.
Oh.
If we did the same thing, sometimes you definitely can't see this on camera, but sometimes I get a paper plate full of compasses and then just put this magnet in the middle. And if we had a compass here, it would line up on that line. If we had
Isn't
a
that
compass
really
here,
the compass?
it would line up, no. It would line up on that line. So the compasses would line up on the lines of the magnetic field. And we could do the same thing on Earth, and it would show us where the Earth's magnetic field is. So the magnetic field is a 3-dimensional area where the magnet is influenced. And here's the last thing. Do you remember talking about gravity? Do you remember what did gravity depend on?
Mass and...
Yeah. Keep going.
Proximity.
Mass and, thank you, that's a good word. Gravity, the force of gravity was calculated as the mass of both objects, mass 1 and mass 2, divided by the distance between them squared, times what we call the universal gravitational constant. Now the force of magnetism depends on the charge of the two objects and the distance between them. I hope you can see the similarities between these two equations. They work in the exact same way, except for one important thing. Magnets can have a north and a south pole. Gravity always attracts. The masses must always be positive. But we can have negative charges. And so sometimes magnets attract, and then sometimes they, what? Yeah, they oppose. What's a better word than that?
Repel.
Repel. I'm going to try not to break my finger by doing this, but there we go. So if I have another magnet here. This, what am I doing? Am I stupid? on, magnet. I think I actually depolarize this other magnet because it's just, I think as I'm
It's the
doing
flat
this,
sides.
but it is, you're right, but it's also completely repolarizing this weak magnet when I bring into the magnetic field of a strong magnet. There we go. So that's, and you can tell because for a while that's repelling, but then as I bring it closer, it's actually repolarizing this magnet. So let's just do it with these other guys. Come here, buddy. You stay there.
Why?
There we go. So these are both south, and here's something important. The south poles of a magnet repel each other, right? Repel.
They just hate each other.
And the north poles of magnets repel each other. Opposites do what?
Attract.
Yeah, you can remember, that's very easy. Opposites attract. So like a man and a lady get attracted. Not always, whatever. But you can remember it that way. Opposites attract. Similar repel. That's why if you meet someone that's just like you hate them. Right, Emma and Dalton? You guys are twins? No.
Wait, Andy.
Do you have questions about any of this?
There's nothing like
Questions? You had a lot of good questions. Faith has one more. Let's hear it, Faith.
How is the magnet getting repolarized?
Oh, good. So what's happening, Faith asks, how is the magnet getting repolarized? I have this strong magnet, which has a strong magnetic field. And here's a weak magnet. And right now it's not labeled. But right now let's say this is the North Pole and this is the South Pole, just because this one also isn't labeled. And so what's happening is right now they're repelling. This is the South and this is the South, with where my thumb is. And they're repelling. But then as I bring it closer, this magnet is strong enough that it's shifting the magnetic domains. All of the electrons of each little atom are shifting the other direction. So it's just changing the direction this magnet is. So now instead of it being this is the South Pole, now it's the North Pole so that it can attract to this magnet. And then all of them switched. Remember, the poles are a directional thing. The atoms themselves don't have to move. They just switch direction, like the compass. Good question. Thank you, Faith. Who else? Do you feel like you have a slightly better grasp of magnets now?
Yes.
Here are some takeaways. You need to know that the force between magnets depends on the charge of the magnets and the distance between them. Okay? It gets weaker the further apart they are. You need to know that magnetism is a field force, which means it's non-contact and it exists in a three-dimensional area around the magnet. You need to know about magnetic domains and what causes magnetism, and you need to know about that magnetism is a force. And one of the four fundamental forces of the universe. Ty.
What do North poles do?
North poles repel each other. Two north poles repel each other, two south poles repel each other, and a north and a south attract. Gabe.
Would you say that the denser the magnet is, the stronger it would be?
I would say that the better lined up the magnetic domains are, the stronger the magnet is. So this magnet, even though they are all mostly facing the same direction, some of them are kind of off. It's just like when you comb your hair and you try to make them all go the same way, but there's still some that are going the wrong way. Same thing with the magnetic. So it'd be the difference between like Gabe's hair and Abby's hair, or the weak magnet and the strong magnet. Most of Gabe's are in the same direction, but there's a couple flyaways. Whereas Abby's are all almost in the same direction, so Abby's a stronger magnet. Or let's use Carson as an example. His would be non-magnetic. There's no hair on Carson's head is going the same direction as any other hair. And so his would be non-magnetic.
I think mine is well.
Oh, and by the way, you don't have to know these vocab words, but the kinds of magnets are permanent magnet, like this. There's something called paramagnetic, which is like the whiteboard, where it will interact with a magnetic field, but it doesn't have its own magnetic field. And then there are electromagnets, which are magnets that only have a magnetic field when they have electricity going through them. There's also something called diamagnetism. There's one other one, but I've forgotten it. Yes.
How do you make a permanent magnet?
I think it has to be one of those things, iron, cobalt, nickel, or some of the rare earth metals. In fact, this one is a rare earth metal. It's a neodymium magnet, which is one of the rare earth metals. Neodymium is number 60 on the periodic table, which is a rare earth metal. And I think it has to do with the way they forge it. So this would have been molten at some point. They would have melted this, and then they would pour it into a mold to be this shape, and then they would cool it in a specific way that all the electrons line up towards each other. They might even cool it in a magnetic field. They have a strong magnetic field, probably electromagnetic field, and then as this cools, the parts of it line up to be in the same direction as that magnetic field, and then when it's shipped off, it still has that magnetism. Other questions? Thank you, Faith. You've been full of good questions today, Faith. What kind of metals are magnetic?
Nickel, cobalt,
iron, and some of the rare earth metals. And here's something interesting about copper before we go. I have this big lump of copper here, which is non-magnetic, and I'm going to pass this around. Not magnetic. Not magnetic, but it will, you can't really see it. If I had a bigger chunk of, can you see that a little bit?
Yeah.
If I do it from too high, it doesn't really work. Copper has a property called magnetic impedance, where, you see that? I'm trying to knock it down.
It goes.
It goes really slow. What it does is the atoms in the copper resist a magnetic change. It's called magnetic impedance. Some semi-trucks use this for braking. But I want you to try to wiggle this around. I'm going to give you another example too. If you just wiggle on your, not Chromebook, don't touch this to your Chromebook, it will wipe your Chromebook and it'll ruin it. But if you try to wiggle it around the table, it goes like that. And if you try to wiggle it around the copper, it's much more, it feels almost like it's in like honey or something because it's magnetically impeding the movement of this magnet. Instead of me passing this around so you don't wipe your Chromebooks, I'm going to have you come up here and take turns doing it. You have other questions? Okay.
So, Mr. Kyle, would you